Hello, hello. Okay, so good evening. Welcome to week 10 of the NPTEL PMRF session on real-time digital signal processing. Today we shall be revising all the concepts of digital speech coding. Why is it needed? Okay, so let's get started. Yeah, so what is digital speech? So basically, you it is the analog speech signal which is sampled and then quantized in an A to D converter and then transmitted in a digital fashion, and the resultant signal is a digital speech signal. Okay, so it's simply analog to digital conversion. And where are the applications? So one of the application is the live streaming which is going on right now. So you have both audio and video. So you have obviously telephone. These are quite trivial now, but there was a time when these things were not trivial. These were state of the art during the early 1950s and 60s. Speech storage, text to speech, which you can get in Google, YouTube, where they use these machine learning algorithms, natural NLP algorithms to convert your text, speech to text, or the other way around. But and why do we go with it? The issues involving the analog speech. So first of all, we need to have efficient use of bandwidth. So there's a huge competition for bandwidth. So what do we need to do? Compress to lower bit rate per user. And what does it do? It increases the number of users, and hence the revenue also increases. Secondly, we also want improvement in speech quality. And how do we determine that? For a particular environment. Okay, so for a particular environment. Okay, so Bharat, so in today's lecture we are talking about digital speech coding. Is my video visible and audio audible? Please let me know through your through the microphone or your chat. Yeah, yeah, Bharat. You have raised your hand. If you want to say something, please speak up. Okay. So now, what do we do? Improvement in the speech quality for a particular environment. And how do you define the environment? Okay, so let me revise it for you. So basically, you're talking about digital speech. And what is digital speech? You see, this is the analog speech signal. We pass it through an A to D and we get a digital speech. Simple. And then what are the applications? Very common: telephone, speech storage, and text to speech, or speech to text. In either way you can look at it. And what are the issues involved in digital speech processing? So basically, you have to ensure efficient user bandwidth, And for how do we do that? We have to compress the bit rate per user. So as a result, for a fixed bandwidth you get more users and thus your revenue increases, but you have to do that ensuring that the quality remains the same. And to improve speech quality in a particular environment, how do we define the environment? We define it by the bit error rate, packet delay, packet loss, etc. All the terms associated with the communication network. Okay. And also as this is a real-time signal processing course, we are quite concerned about the hardware complexity. So speed sorry, the speed, the coding or decoding delay, we'll look into greater details today. Speed, delay, computational requirements like how much power it will consume, how many multipliers, adders, all that stuff that we talked about in the beginning of the semester. And power requirement. Fine. For wireless systems, which is the state of the art, in 1G first generation wireless systems we used to have analog speech transmission, and from 2G, 3G and more and more G's coming up, we have digital speech. So the advantages of digital speech is more or less the same as the advantage of any digital system, which includes increasing the system capacity. You are using digital systems, you are able to store it, and then you can improve the quality of speech by using error control coding, equalization, which is very difficult in analog, because analog systems, the systems themselves will inject noise into the system. You can also improve security, which is absent in analog systems. You can introduce security by encryption and all that stuff, crypto stuff. You can reduce the cost automatically. Digital means low cost. Okay, so now we are moving a bit into the communication system side. So let me draw the diagram of a typical wireless communication system. Okay, so first of all we have the source. We are assuming all of them are electrical sources. So basically my voice is taken up by a sensor. So the sensor is a transducer which converts the acoustic pressure signals into the electrical signals. So that kind of intermediate stages are being collapsed into a single electrical digital source. So you have a source, then what you do, you encode it, source encoder. So what is the source encoder used for? The source encoder used to make to take advantage of the entropy of the source. So a source emits different symbols, so each of these symbols have different probabilities, and correspondingly based on the probabilities you can assign word lengths to them, and by using Huffman coding or all those coding techniques you can achieve low word length for a given symbol that is being sent. So you use lower data rate. Second, you do channel encoder. Now so basically in source encoder you are kind of reducing the length, you are reducing the redundancy. Okay, but in channel encoder what do you do? Channel encoder is opposite. Now channel as we know is an unreliable system. So basically you shall basically all the impairments of the channel can flip the bits of our system. Okay, so in order to ensure that our data remains immune, we do channel encoding. So introducing redundancy in the system for reliable transmission of data. Then you have a modulator, so in order to ensure that you are able to send off the symbols properly. Then you have the actual channel, and with the channel comes all the impairments. If you want to read detail, you have lot of NPTEL courses on communication systems, refer to one of them. Then you have channel decoder. So whatever path has been traversed from source to source encoder, you up till the channel, now you have to undergo the reverse direction and the inverse of all the operations. So the channel decoder, which brings back the which uses the inverse of the channel encoder, similarly source decoder, and finally you reach the destination. Okay, I am sure you must have studied this in a digital communication. So that was a typical wireless communication system. So some of them we might be requiring in today's discussion. So what are the, since we are talking about speech signal today, what are the characteristics of speech signal? Okay, by the way, let me mention that in case you have any doubt, please feel free to stop me in the middle. Okay, and you can ask me any doubt if required, or you can type in the chat box as well. First of all, it's the bandwidth. How much is the bandwidth? So mostly the energy is concentrated between 20 Hertz to 7 kilohertz, and human ear is sensitive between 50 Hertz to 4 kilohertz. Okay, and in time domain, what are the characteristics? So in time domain, first of all, the samples are highly correlated. So I should write high correlation, which we had talked about quite in a great detail about correlation in our maybe week 7 or 8, right? So each of the samples are correlated with one another. So you have very high predictability of the next sample given the previous samples. And then you have something called short term stationarity. What does it mean? It means that for short intervals, so suppose I am speaking, so when you record speech or you record sound, you will get to see some kind of envelopes corresponding to each of the things that you pronounce, each of the alphabets, each of the vowels. Okay, so for each alphabet or vowel or something called phoneme, you have this kind of a waveform for certain duration, then some gap, then another waveform, each of them differing in their characteristics. But within each of these short intervals, the statistics of the signal remain stationary, the mean, the expectation. Okay, so whatever you learnt about wide sense stationary, so wide sense stationary means throughout minus infinity to plus infinity, but in this case that holds only for short intervals of time that I am circling over here. Okay, so, but if you see for long intervals, if I collect 3 or 4 vowels, then that kind of statistics it does not hold true. Okay, and we can classify speech, human speech we are talking about, into 4 categories. First one is voiced, is created by air passing through vocal cords like a, v, v. Okay, then you have unvoiced, is created by air passing through mouth, maybe the lips, mouth and lips, like S and F. Then you have mixed or transitional, and you move between voiced and unvoiced, and then you have obviously silence. So basically voiced uses vocal cords, whereas unvoiced does not require the use of vocal cords. Okay, so now that's the basic about speech signal. Now we move on to something called speech coder. So what is speech coder? It is a device that converts speech to digital signal. So it's not just the ADC, actually it includes the parts, the digital processing after the ADC, that converts into some kind of a desired form that exploits the characteristics of a typical speech, human speech signal. Okay, so how do you classify speech coders? Basically you have waveform coders, you have vocoders, or also known as parametric coders, as well as hybrid coders. So what do waveform coders do? Convert any analog signal to digital equivalent. What do vocoders do? So waveform coder are a direct correspondence, a one-to-one mapping. You have some kind of analog signal, simply convert them to digital equivalence, I mean directly sample to sample conversion, that's it. Vocoders are a bit different, try to exploit special properties of speech signal to reduce bit rate, and then you build a model or a structure of speech, and then transmit parameters of that model. So basically what you do, you assume that your speech has some kind of a relation, maybe a discrete an IIR relation or an FI relation or a mixed relation. So those relations will have some coefficients, some variables. So rather than transmitting the signal as a whole, you transmit those parameters, and then you can understand very well, rather than if you are transmitting parameters, you are taking up less number of bits. Okay, so at the receiver side you take back those coefficients and simply decode the entire signal back based on the parameters. You reconstruct the signal back, but then you understand one problem, right? The structure of the signal is an approximation. It may not be true always, it may not be perfect always, and moreover, since you are transmitting over a channel, so you have the issue of robustness. So if your coefficients which are being transmitted, if they undergo some kind of impairments in the channel due to the channel let's say noise or channel fading or whatever, okay, you can look into detail in the digital wireless communications course. So those impairments can manipulate or bring errors into the coefficients. So when at the receiver side you use those defective coefficients, you at the end of the day you get the defective sound. Okay, so the robustness is low. And hybrid coders, what do? They combine features of types of coders. Okay, so a bit of waveform coding and a bit of vocoding. So let's talk about waveform coding. Any doubts till now? Please let me know. Okay, so basically what you do, let me give an example. ADC based analog to digital conversion. Then what do you have? They have the signal sampled at Nyquist rate and quantized uniformly. So, and what does it mean to quantize uniformly? You mean to say that all the samples have some equal number of bits, n bits, and the type of quantization is the same for all. And the most popular and common example for waveform coding is PCM, pulse code modulation, which is generally taught in the digital communication systems. For an example, for speech, the maximum frequency is generally 4 kilohertz. And what do? We pass speech through something called a mu law compander. We'll tell very soon what is this compander. And the sample rate is how much? 8 kilohertz, and generally take 8 bits per sample. So your net data rate is 64 kbps, so 8 bits per second. And what are the characteristics of such a waveform coder? So the quality is high. As I mentioned, you are sending the speech directly. Complexity is obviously low because you are not using sophisticated transforms or any kind of digital structures. High bit rate, yeah, that's one thing. You are sending stuff as it is. We are not exploiting some kind of redundancy or anything. Low delay because you are not using too much electronics, and high robustness. High robustness with respect to the other schemes, the parametric vocoder, which we will study next. So a bit about PCM speech coding. So it is a International Telecommunication Union based General G700 standard used in public switched telephone networks, or also known as PSTNs, for speech coding in the 1960s. Okay, and it includes analog compounding and PCM. So how does the structure look like? Block diagram: analog input, filtered, then you have an analog compressor, then you have the sample and hold circuit, you have the ADD converter. Finally it goes into the channel directly, no encoding, no decoding, nothing in that such. Then you have the DAC, you have the hold circuit, then you have the opposite of the analog compressor, which is the expander, compressor or compander I am writing, in the analog expander, back to BPF, and you have your analog output. Mu law compander, you also have mu law expander. What you get initially at the sample and hold circuits are the PAM pulse amplitude modulation signal, and after you convert them to digital you have the pulse code modulation. Okay, so what is compending? Compending analog compander emphasizes small values, de-emphasizes large values in order to equalize SNR across samples, and you do the exactly the opposite in the expander. So the analog compander for the mu law has a function which is given like this: sine of, this is the input S, log of 1 plus mu by log of 1 plus mu. So let me draw the output versus input relation. Output, input, one. So let's say if there is no compending, it's orange. No compending. Then let's suppose I have mu1 equal some mu1. Then if I increase the mu1 to mu2, we have something like this. If I increase it further, I get something like this, mu3. So as you can see, as your mu increases, increasing mu, you move more and more towards the saturation kind of behavior, and this orange one is when you have no compending. Okay, so basically you can see over here that for very small values the gain is extremely high for a large mu, and then for large values of the input, means close to 1, you have negligible gain. Okay, okay, now we look at PCM speech coding. So previously talking about analog compending, now digitally companded PCM system, which is a ITU G.711 standard. So what does it have? Better quality speech than analog companding. Then you have differential PCM. So it's a modified version of PCM. What happens over here? You are able to reduce bit rate from 64 kbps to 32 kbps. So what do you actually do? That since samples are highly correlated, you transmit sample difference rather than the samples themselves. For example, let's say we have 13, 14, 14, 15, 12, 10, 15, 14, 14. Okay, so let's say we're starting with 13. So initially you have to size 10, 13, but after that 14 minus 13, which is 1 difference. See, here there is no change, so it's 0. Here there is 1 increase, then here there is 3 decrease, here there is 2 decrease, here there is a 5 increase. Okay, so as you can see over here, you are not sending these large numbers, you are sending much smaller numbers, so you are using lower data rate. Fine. Okay, so and some more thing that you can do is adaptive DPCM, which adaptively adjusts the range of quantizer, and what happens as a result of this? The quality gets improved. ADPCM ITU G.726. So the circuit over here, not circuit, the diagram over here is quite just hold a second. Okay, so what we shall be doing over here is that we shall be oh, I think I have to yeah, so it seems I have to write once again. So you have analog input band pass filter, you have the sample and hold circuit, then you have the A to D converter, you have a digital compressor or you can say digital compander, then you have the channel, then you have the reverse components, digital expander, you have the DAC, you have the hold circuit, then you have the filter, finally you get the analog output. So this is the PCM transmitter and this is the PCM receiver, and we are talking about the differential PCM wherein you send the differences and not the normal samples as it is. So if you look at DPCM transmitter, you have the analog input, low pass filter, then you have a difference block. Okay, so a plus sign over here and minus sign over here, you have the A to D converter, you have an integrator over here, DAC, encoded. So there is a difference over here, you can see the difference in negative symbol over here, right? So you are encoded, sending encoded difference samples, right? So how will the corresponding receiver look like? This is the DPCM receiver. So we have the DPCM input. Since it is digital, now you convert it to analog. First you have a DAC, then you have a summer, you have a hold circuit where you are actually doing some kind of a corresponding summation of xi plus xi minus 1, that kind of a thing. And then because you have hold circuit, you have some kind of a staircase kind of a waveform. Now in order to get away from those jumps, use a low pass filter and you get the analog output. Now some alternatives of in all these signals we were considering the same kind of a frequency spectrum. Okay, so do you want to say something? Your microphone is on. Okay, fine. So what we do is subband speech coding. So after you left, we are actually talking about the same and deep in the PCM receiver and transmitter. Then we showed the transmitter as well as the receiver for the differential PCM over here, you can see. Now we'll talk a bit about subband speech coding. What happens in subband speech coding? We partition the signal spectrum, okay fine, spectrum into non-overlapping frequency bands and use different ADCs for each bands. Okay, so it's you divide the spectrum into several portions and then individually you work on them. So that actually helps when your signals are colored, especially speech signal. So when you kind of do work on an individual frequency range, so that improves the efficiency, because of the statistics of the signal, it become almost behaves like white noise in that case. So for example, let us consider three bands, band, their range, and how many bits we encode them. One first band, second band, third band. Okay, first one ranges from 50 to 700, second one is from 700 to 2000, the third band ranges from 2000 to 3400, and the first one we encoded by, let's say, 4 bits, second one by 3, and third one by 2. Why is it so? Because higher frequencies are less prevalent in our speech than the lower frequencies. So when I sample the first band, what's the data rate? 2 times 700 Nyquist rate, so 1400 Hertz, and you are using 4 bits for each, so 5.6 kbps. Second band has a maximum frequency of 2000, so you have 4 kilohertz sampling rate, and each encoded by 3 bits, so 12 kbps. And the third band has 3400, so you have 6.8 kilohertz, 2 bits for each, so 13.6 kbps, so you have 31.2 kbps. Okay, rather than utilizing 4 bits for all and then same kind of thing, you are reducing the bit rate. So the scheme that I am talking about, so analog speech, band pass filter 1, band pass filter 2, band pass filter 3, then you have corresponding to each of them, signs should have been opposite, you have the ADC1, ADC2 and ADC3. Each of the ADCs are operating at different sampling frequencies that I have shown over here. Okay, and their outputs are then multiplexed properly and then sent for channel coding. And this kind of a structure where you have different frequency zones, and each of the frequency zones have their own processing ADCs, we call it something as the frequency interleaved ADCs. And the mux will not be a normal mux, it will have a good deal of digital filters involved in order to compensate for the band pass filters, because they are not ideal. Okay, so that's all for waveform coding. Now we will go to vocoders. Just hold on a second. So now we'll study about, let's change the color, vocoders. Okay. So vocoders are parametric coders. So in other words, it encodes the parameters. So what do? You model vocalization of speech. How is that done? First of all, speech is sampled and broken into frames of, let's say, close to 25 milliseconds. And what do? Build speech model. I mean, it's already built. You consider some kind of a model and you transmit the parameters of that model, and then at the receiver end you synthesize approximation of the speech using the parameters that you have received. And the frames that I was talking about, as you can see over here, I was talking about short-term stationary a while back. So these frames, these are the frames that you can take individually, and these are the envelopes, these are the structures that I are going to model. Okay. So the first vocoder that we are going to talk about is the important one, is the linear predictive coder, or LPC. What does it do? It models our vocal tract as a filter. Okay. And how is the vocal tract or the filter excited? It must have an input, right? So for voiced speech, the input is a periodic pulse. It is a model, it's not a reality. It's a model that quite nicely models our speech production. And then unvoiced speech is as if is the filter excited by noise. And what are the transmitted parameters? First of all, it's the filter gain, then is the voiced or unvoiced, whether it is voiced or unvoiced. Based on that, the kind of input will be given. If it's voiced, the periodic pulses will be provided as input, or else the noise will be provided as input if the unvoiced decision is true. And if it is voiced, we will send the pitch if voiced. And let us see a block diagram of this. You send the pitch period to the pulse generator, and this is for the voiced case. For the unvoiced case, you get it from the noise generator. So here is a multiplexer which can shift between either of the two, and what drives this is the excitation selection. Then you have the gain factor G. Okay. Then the output signal mu t. What do? this is the excitation model, and then this muti goes, this is the, and the right side that we are going to draw is the vocal tract model, except the muti, and you have some kind of a filter which is obviously linear feedback, and then some coefficients of the filter which we call as the predictor coefficients, and what we get over here is the output. Okay, so this is the LPC, linear predictive coder, speech generation model. Fine, so that's how we assume that the speech is being generated in our vocal tract. Okay, now let me give an example in order to make things clear. Example, so let's take a 10th order LPC. So we sample it at 8 kilohertz and we buffer 240 samples, which is by 240 samples we mean those short bar frames we are talking about. So correspondingly the frame length is 30 milliseconds. And what is the filter model? The filter which we had shown in the linear feedback path is the h of z equal to g plus 1 upon summation k equal to 1 to m bk z to the power minus k. So let us note down each of the terms. M, which is the filter order, is known to all beforehand, it's 10. G is the gain which we send, it's let's say 5 bits. Bk is the filter coefficients, 8 bits each, and we have 10 coefficients, so 8 into 10, which is 80 bits overall for coefficients. And whether it is voiced or unvoiced decision, that's obviously a one bit. You get 0 for unvoiced, 1 for voiced, or anything else. And the pitch that we are talking about, that is 6 bits. So as a result you have 5 plus 80 plus 1 plus 6, that's 92 bits, and you are transmitting it in 30 millisecond. So what is the corresponding data rate? It is 3.067 kbps. That's much lower than the waveform coders that we had seen. Vocoders provide tremendously low data rates, and that's really helpful. So in general, LPC coders can achieve around 1 to 4.8 kbps low data rates. So you can really understand that since we are doing some kind of an approximation, the quality of the speech will be low, and the complexity has been increased to a certain extent because we are doing all these modeling of speech production from noise or periodic pulse, then all the filters. Low bitrate, which is a very good advantage. Delay has increased, and robustness has decreased, because if these coefficients get affected during transmission, then you're bound to get poorer outputs. So what happens is that the quality is very bad for telephone communication. So what was used during those days were hybrid vocoders. And how can you improve the quality? Other way, you can increase the modeling. You can make a better model for the speech production, refine the model, and you can also improve the inputs to the speech coder. Rather than using just two kinds, you can use more kinds of input rather than just noise and periodic pulse and all that. Then we look at an improvised version of vocoder, that is the RELP, or residual excited LPC vocoder. Fine. So what does it do? It improves the LPC quality as it's shown by transmitting the error, also called the residue, with the LPC parameters. So you have the signal, you buffer them into frames, okay, like buffer 240 samples. Then we do the signal analysis, where you understand the parameters, voice, unvoiced, decision, gain, pitch parameter. And then we do the synthesis directly, and this is at the transmitter side itself. So using the parameters that we have obtained from the analysis, we generate the synthesized signal, and we also have the original signal, so you can directly get the error or the residue. Okay. And then both the encoder takes the error as well as the parameters, and we get the output. Fine. Now let's talk about GSM speech coding. GSM meaning the GSM technology which was used earlier, 2G, 3G days, 2G days. So what does it do? It uses RPE, or the regular pulse excited LPC. So what is so much different about RPE? So LPC, it combines the differential PCM which you are talking about with LPC. Then so information from previous samples are used to predict current sample. Some kind of a predictor is there, and when you have the current sample and the predicted sample, you take the error and you transmit the error. Moreover, the LPC coefficients and error is transmitted. Understood? So you have analog speech, low pass filter, ADC, 8 kilosamples per second, 13 bits per sample. So you have 104 kbps. You have an RPE, LPC, LTP encode. So LTP actually stands for long term prediction. So these are technology jargons, and then because of this encoder you send data 13 kbps rather than the 104. You have channel encoder. Okay, so what happens in the channel encoding? The 13 kbps is actually 260 bits in every 20 millisecond frame. Okay, so this 260 bit per 20 millisecond goes into some kind of a demux. Okay, so there are three classes of bits. So there are 50 class 1A bits. We'll tell you very soon what is class 1A or something. Then it uses 3-bit cyclic redundancy check codes, and it increases to 53 bits. Then you have 182 class 1B bits. Then you have 215 convolutional coder. Okay, not discussing in much detail about these convolutional coders because I am not from that field and this is not a communication systems course. And then you have 78 class 2 bits. You have 470 bits over here, and then you do some kind of a bit interleaving, which is managing the bits, playing with them, and then you get 22.8 kbps. Channel encoding increases the data rate because you're sending extra bits. So class 1A bits undergo CRC plus convolutional coding. Class 1B bits undergo only convolutional coding, and class 2 bits they have no error protection. You don't do any channel encoding on them, and that's most likely because these are for not so significant in information. Okay, so that's it about the basic vocoders. We shall now study about hybrid vocoders. So in first we have codebook excited LPC. So as I mentioned earlier, the problem with traditional LPC model, where you have all the voiced, unvoiced, speech, voiced, unvoiced, gain, whether it is those parameters. Let me go back and show you what I mean. Gain, voiced, unvoiced, and the pitch. Okay, so these kind of modeling was done. So these things don't model transitional speech. That means something which moves from voiced to unvoiced or unvoiced to voiced, intermediate ones. Okay, well, so what do we have? We have a code book approach. Pass speech through an analyzer to find closest match to a set of possible excitation, and this set of possible excitations is what we call as the code book. So what we actually transmit are the codebook pointer, I mean which entry or which excitation was matched closely. So you have a codebook at the transmitter and the receiver as well, plus the LPC parameters obviously. And industry norms, industry standards, once again NATDMA, time division multiple access, if you have read or heard somewhere in communication. Into 95 3G ITU G.729 standard. So you can have either the pulse or the noise. You pass either of them, both kind of inputs, into the codebook generator, and that drives the synthesis filter, which we had been talking about, the filter parameters, get some kind of output. So this is the multi pulse excitation, and this is the stochastic excitation. Okay, so now I shall draw a big diagram of a typical codebook excited LPC encoder. Typical codebook excited LPC encoder. So first we have speech input, summation block. So speech goes into the coefficient predictor block, goes into a gain predictor block, all that we had mentioned earlier. Then we have the linear predictive filter, gain. So the coefficients go to linear predictive filter, the gain predictor goes to the gain block, and then the speech is subtracted. No, the predicted input or the predicted output is subtracted from the speech to check for the error. So we do error weighting and minimization. Okay, and then based on that go to the excitation codebook to see which one is the best, and this also drives the gain block. We have a multiplexer to send in all the information that we have predicted, the gain, the coefficients, and the excited notebook pointer. Okay, this gives us the output. So similarly, as we had talked about subband speech coding, we can also have subband LPC codebook excited LPC filters, predictor vocoder. So we have NATDMA IS54 speech coder subband codebook approach termed vector sum excited LPC or VSE LPC. So you have codebook 1 gain 1, codebook 2 gain 2, codebook 3 gain 3. You add all the in these, each of the codebooks are for different subbands, and then you match add all subbands output, pass it to the synthesis filter, then you get the output. So actually IO1 gamma 1 L gamma 2 H gamma 3, and you also have the betas and the filter coefficients. Okay, fine. So now we will see how we evaluate various speech coders. Evaluating speech coders. First of all, we do a qualitative. What is done is a qualitative comparison. Basically, you call in a lot of people and then do it based on, and all of these are industry standards. Everything is documented well in the ITU books. Yes, in recommendation ITU T-Rec P830. So one possible category is the absolute category rating, where subjects listen to samples and rank them on an absolute scale. Result is a mean opinion score or MOS. It's not the metal oxide semiconductor, it's mean opinion score. So the MOS has 5 categories based on the sound: excellent, good, fair, poor, bad. So people will come and give the speech sample a rating of how they felt. It's absolute in nature. 5 4 3 2 1. And then there is another category which I personally feel is better, because, and it's in general better because you do comparison. So I say something is good, A is good and B is good. So how do you say whether A is better or B is better? So you have to do compare them, right? So you have comparison category rating. So what happens over here? Subjects listen to coded samples, which means all the LPC and all coding you have done, listen to that output, and original uncoded sample. The two are compared on a relative scale. Result is a comparison mean opinion score, or CMOS. It's not complementary metal oxide semiconductor, it's comparison mean opinion score. This is not semiconductor electronics, so don't get confused with this CMOS. So in CMOS, okay, it's complete, it's audio, it's not semiconductors. These are the ratings: much better, better, slightly better, same or almost same, slightly worse, worse, much worse. So much better is 3 2 1 0, -1 -2 -3. And the important thing is that results vary a bit with language and speaker gender. It's quite obvious. And now let me note down certain coding standards and their corresponding bitrate as well as the MOS scores. Standard speech coder, bit rate, mean opinion score. PCM is a waveform coder. 64 bit rate will always be in kbps, in this case 4.3. this is actually the best one. Then you have something CT2, it's adaptive differential PCM, 32 kbps, 4.1. Then you have DECT, this is also ADPCM, 32, same. Then you have NATDMA that I was talking about, so it uses hybrid coding, VS variable excitation, variable sum, something like that we are talking about, 8 kbps, and MOS is 3. So you see, if when you go for the hybrid codings, we lose upon the MOS scores. GSM that we talked about, it also uses this, it uses hybrid RELPC, the residual error one, 1.3 kbps, so it has 3.54 MOS, not as good as the PCM one. Then QCELP, it is the hybrid codebook encoded LPC. You have two possible data rates, and the MOS score ranges from 3.0 to 4, and you have the ideal, or not ideal, the primitive LPC, which is a pure vocoder. It has a 2.4 kbps and it has the lowest possible MOS. So you understand very well, it is poor MOS. So you understand very well that you can never use a vocoder alone. You have to use some kind of a hybrid, or introduce a bit of the original signal in terms of the error signal. Okay, some kind of a waveform encoding is required. Now when you are testing the coder quality, you need to consider background noise. Background noise for testing coder quality. So first one is clean or no background noise. Then you have vehicle noise, you have street noise, and you have combination of the two. And the environments for the noise can be, what will they simulate? Perfect, where there is no transmission error. Then you have random channel errors like the AWGN, where you have randomly inputs coming in. Then you have bursty channel errors, which happens in cases where suddenly you have errors, then the noise being injected, then no noise, in 1 second you have noise, no noise. Errors come, or the noise comes in bursts, which happens in certain scenarios of communication. Now we have talked about the coder decoder selection. So for cellular codecs, we need to consider quality, complexity, delay, and compression rate. So let us look at some standards. ITU coder bit rate, the coding delay, coding delay, decoding delay, and the complexity. G.711, G.729, and G.723 A and B. 64 kbps, 8 kbps, and then 6.4 kbps and 5.3 kbps for A and B respectively. There's no coding delay in the first one, second one is 15 milliseconds, third one is 35.5 milliseconds. So these are all pure data. It's no engineering involved in it. These are pure standards. Complexity low, medium, and high. And for 3G standards, there are two competing codecs that use multi-mode CELP, the codebook excited vocoder. One is the 3GPP CDMA 2000, and the other one is 3GPP UMTS. Okay. Finally, we have talked about the four kinds of sounds: the voiced, the unvoiced, transitional, and finally we have silence. Now we will conclude with the silence. uh, Silence, compression, %40 of speech is silence, so no need to transmit during those phases of silence. So there are some terms associated with it. One is VAD, voice activity detector. What is it? Hardware to detect silence period quickly. Then you have variable bitrate coders, which significantly reduce bitrate when silent. And then you have something called DTX, or discontinuous transmission. So you stop transmitting frames, you actually send minimal number of frames to keep the connection up. Then you have comfort noise generator, or surprisingly it's also called CNG, not compressed natural gas. So what does it do? It synthesizes background noise. And why is that done? Because if I'm silent for a while, then you may think that I've cut the call, okay, or I'm not there, but I'm still there on the call, I'm not speaking something. So in order to ensure that you don't feel that the call has been cut, there's some kind of a noise, light noise generated, that isn't discomfortable. That's why it's called comfort noise. It's random noise. For example, if you keep quiet or just here, you will get some low noise in this meeting, okay. You won't get this noise if you leave the meeting. Random noise, or reproduce speakers ambient background. As an example, GSM codec and voice over internet protocol, or V2OIP G.723.1 codec has voice activity detector, discontinuous transmission, and comfort noise generator, whereas CDMA 1 and CDMA 2000 codec use variable bit rate approach. So how does it look like? So let's say our speech envelopes are something like this. Okay, so actually this is actually how your speech oscillates, and these are the envelopes. This is our speech. So if you actually use variable rate, so what will be the rate like? So during the moments of speech it will be high and it will decrease, and then immediately it will fall down. Once again it will send, and depending on time it will go up and then down. So you see, corresponding to each of these time durations you have the corresponding data rates. Okay, this is the variable rate approach. And finally we have the fixed rate with voice activity detector and DTX. So you can see during times of speech I have no, it should be 0 actually, don't transmit anything, but during times of speech during times of silence you don't transmit anything, and during times of speech you transmit. Okay, this is fixed rate with VAD and DTX. Okay, so that's it for today's session. Thank you very much, and we will have our next week 11, where we will be covering the last topic on image processing. Actually it's not image processing, image and video processing, basically on discrete cosine transform and JPEG. And week 12, although the content is completely lab oriented, I will do a 2-hour revision, and then there will be another revision session. It won't be on a Monday because it coincides with Navratri, so I will do somewhere before that main time. Okay, thank you.